Welcome back to Math TV with Professor V. This is part 2 of the video on optimization for Calculus 1. And we're going to be focusing on examples that pertain to economics in particular. Woo. Okay, so just keep in mind, we have to identify what quantity we're trying to optimize, write a function for it using one variable, and then take the derivative, get our critical values, verify. So I'm just going to jump right in. If the price charged for a candy bar is P of X cents, then X thousand candy bars will be sold in a certain city, where P of X equals 24 minus X over 22. How many candy bars must be sold to maximize revenue? All right, so what quantity are we trying to optimize? Revenue. And just for those of you who don't have too much econ background yet, revenue is equal to price times quantity. And that should make sense. Revenue is total amount of money coming in. And so you take however many units you're selling, that's the quantity, and you multiply by the price. They gave us here the formula for computing price in terms of quantity, X. X is being measured in thousands of candy bars. Technically, this right here is your demand equation. You don't need to know that to solve this problem, but that's what it is. Okay, so can we write a function representing revenue in terms of just one variable, most likely X? Sure. So revenue is R of X, and that equals price. Well, they gave me the formula right here. They gave me the price function, 24 minus X over 22, times the quantity, times the number of candy bars sold. The quantity is just plain old X. Oh, okay. So now let's distribute cleanup. That way we can write our revenue function in a way where we can take the derivative easily. So it's 24X minus X squared over 22. I'll write that as 1 over 22X squared. All right, here's our revenue function. Good. Okay, now we need to optimize it. We need to figure out the max revenue. Let's take a derivative. R prime of X is going to be 24 minus 1 over 22 times 2X. So what's that going to give us? 24 minus 1 over 11 times X. Critical values come from where R prime of X equals 0 and where R prime doesn't exist. It's a polynomial, in particular a linear function, so it exists everywhere. I'm just going to set it equal to 0. So that means 24 minus 1 over 11x is 0. That means 1 over 11x is 24. So x equals 24 times 11, which is 264. And x is in thousands, so technically that's 264,000 when we give our final answer. Now, I do need to verify, though, that this critical value yields the max revenue. So let's go ahead and use our second derivative test. And I'm just going to write verify x equals 264 yields max revenue. So let's go ahead, one more derivative. Here's the first derivative, r prime of x. Let's take a second derivative, r double prime of x. Derivative of 24, that's just a constant. Derivative of negative 1 over 11x is negative 1 over 11. And I can see already the second derivative is always negative, which means my revenue function is concave down. So the critical value where the derivative is 0 indeed is a max. So we are good to go. All right, so let's make sure we answer the question now. It says how many candy bars must be sold? Okay, it's not 264. The answer is 264,000 candy bars. All right. And you know, it's kind of funny, when I first learned about this, when I was studying econ, it felt backwards to me. I was like, really? Companies sit around and figure out how many units or items they need to sell to maximize revenue. And then based on that, they'll go, this is your X, right? They'll go set the price. That was mind-blowing to me. Maybe I was just an oblivious teen. Okay. This next one, it's not so econ-y, but it just has to do with minimizing cost. So I felt like let's throw it in here. A rectangular field is to be enclosed on 4 sides with a fence. Fencing costs $5 per foot for 2 opposite sides. So $5 a foot here and here. And then $7 per foot on the other sides. They didn't say why some sides are pricier. Maybe I'm going to add to the story, okay? This is through the marshland. It's very difficult. This is easier to fence. I don't know. Find the dimensions of the field of area 870 feet squared. That would be the cheapest to enclose. So what are we optimizing? We're trying to minimize cost. How do I know that? The word cheapest. Yeah. Okay, so we want to minimize cost of fencing. Okay. So how would we describe or come up with the formula that represents the cost of the fencing? We need some variables here. I'm going to call these sides X and these sides Y. So let's see if we can come up with the cost function, okay? So the cost, well, let's see. We've got X and another X. So we've got 2 X's, and however long they are, they cost $5 a foot, right, to fence. So that's going to be 2 times X times 5. That's the cost to fence those sides. Then over here, I have Y and another Y. I have 2 Y's, so plus 2 times Y, and each of those sides cost $7 a foot. So cost equals 10X plus 14Y. Okay, remember, whatever quantity we're trying to optimize, we need to take its derivative. So it needs to be a function of just one variable. And right now I've got 2 variables. We got to eliminate one of them. Can you see some info we haven't used yet that will let me do that? Why, yes, they told me the area of the field is 870 feet squared. So what does that have to do with the problem? Not much, but it's just going to help us relate X and Y so I can cut down on how many variables. We know area equals X times Y, so that has to be 870. And then it's up to you now. Do you want to eliminate X or do you want to eliminate Y? I mean, here it would be equally easy, whatever you chose, okay? Let's just solve for Y in terms of X. So 870 over X. You could do the other way around though, it'll be fine. Okay, so now I can write cost as a function of X. It's 10X plus 14 times 870 over X. I know. And then, sorry, dropped my calculator. C of X is going to be 10X plus, I just want to make sure, 14 times 870 is 12,180, and then I'll write this as X to the negative first. All right, very good. Here's cost function. Now, let's go ahead, take the derivative so we can get our critical values. So C prime of X is going to be 10. Then remember, this exponent comes down in the front, so then we'll have minus 12,180 X to the negative second. Good. Now, to get our critical values, usually we want to put all our variables with negative exponents in the denominator and then get a common denominator. This is very important when you do graphing problems. When you do optimization, usually you don't need to be so precise, but I'm just going to do it so you guys keep up good habits, okay? So here's my derivative. Now, critical values come from two places where the derivative equals 0 and where the derivative does not exist. Now, in this case, the derivative does not exist if x squared is 0, which would mean x is 0. But that's not in the domain of the problem, okay? So, I mean, yeah, of course it would be the cheapest to enclose this field if you don't even get any fencing, but we gotta enclose the field. We have to do what was asked of us. So we're only interested in the case where c prime of x equals 0. And that happens when the numerator of your derivative is 0. So that would be 10x squared minus 12180 equals 0. So then we have 10x squared equals 12180. X squared is 1218. So x is square root of 1218. Does that simplify at all? Let's see. I'm just going to leave it like that. Okay. So from here, what we need to do is verify that that yields a min. And let me add a little page since I'm out of space here. Okay. So verify that x equals rad 1218 yields the min cost. And again, second derivative test. So here's my first derivative. Okay. I'm going to use that version to take a second derivative. So c double prime of x. Derivative of 10 is going to be 0. Then when I bring this 2 down in the front, it'll be positive 2 times 12,180. 12,180. 24,360 x to the negative third, which is 24,360 over x cubed. And then you could see whatever you plug in for x, as long as it's not negative, the second derivative will be positive. So I'll just say it's positive, which means our cost function is concave up at that critical value. So indeed it yields a min, okay? Then let's make sure we answer the question. They said find the dimensions of the field that would be the cheapest to enclose. So we have x. So x equals rad 1218. And then we need to find y. And if you'll remember from earlier, y is equal to, where is it? 870 over x. So y would be 870 over rad 1218. Okay, and then, I mean, if you have to leave it as exact answers, then you would say y is 870 over rad 1218 and x is rad 1218. Since we came up with x and y, you want to tell them which is which. So for us, x was at $5 per foot, and then y was that many feet at $7 a foot. Okay, if you want a decimal, well then let's do it. So rad 1218, that's going to be about 34.9 feet at $5 a foot. And then y is about 24.9 feet at $7. Okay, if you're in my class though and you have no calculator, then you just leave it like this. Good, good, good. All right, last example, and this one is a little tricky if you have no econ background, so I'll give you the background you need right now. Find the optimum number of batches to the nearest whole number of an item that should be produced annually in order to, and they're telling us, minimize cost, if 60,000 units are to be made, and it costs $4 to store a unit for 1 year, and it costs $600 to set up the factory to produce each batch. Assume that the units of this item will be sold off throughout the year, so the cost equation will use the average cost. That's important. So let me explain what's going on, because this can be very confusing. You have a factory and you need to make 60,000 units, 60,000 items over the course of a year. Should you make them 6,000 at a time, 10,000 at a time, 100 at a time? Because when you make them, okay, you don't want to make all 60,000 at once, most likely. It costs $4 to store the items, each item, for a year. And every time you make a batch and you start cranking out batches of items, it costs $600 just to set the factory up. So there has to be a sweet spot. You don't want to store stuff for too long. So you don't want to make all 60,000 at the beginning of the year, right? But then you don't want to be making like such small batches, because it costs $600 every single time you make a batch. So you don't want to make them in like groups of 100. That probably is not going to be a good idea. So it's like, how many batches, how many times should I set it up and tell the factory it's go time? How should I break up this 60,000? I don't know. So let's let X equal the number of batches. Okay. And we're trying to make 60,000 units total. So how many units are in one batch? Well, 60,000 divided by X, right? So say you make 10 batches, then in each batch you would have 6,000, because you would take 60,000 divided by X. That's how many you're making each time. All right, now what did they tell us? We want to minimize cost. At least they told us that very explicitly. So let's figure out what costs go in to all of this. There's a setup cost of each batch. How much is that? Did you catch it? $600 to set up each batch. So if each batch we have X batches, that's going to be 600X. Now, what is the storage cost for each batch? This is where it gets a little tricky. It says it costs $4 to store a unit for 1 year, but not all of the units are going to be stored for a whole year. The first batch might be, but then the second batch is going to be stored for what? 11 months, 10 months, depending on when you produce it. So it seems like, oh my God, there's a little too much going on right now. No, they told us that we could assume that units will be sold off throughout the year, so the cost equation will use average cost. And here's the important idea here. I have just like a little diagram for you guys to look at, okay? When we make the assumption that the problem told us here that demand is constant, then the quantity of the stock, the quantity of your whatever units you're making, can be seen to deplete at a constant rate over time. Okay, so throughout the year, you can assume that the units are being sold off at a constant rate like this. And when inventory reaches 0, then an order is placed and then it just replenishes like this. Okay, so what happens is the storage cost or the holding cost of all of your units is calculated by finding the sum of the product of the inventory at any instant and the holding cost per unit. And so all you need to remember is you just slap a half. You slap a half on there, and then you have $4 for 1 unit. So $4 times how many units are there per batch? 60,000 over X. So that's the number of units in a batch. And then the 1/2 times the 4, that's your average storage or holding cost per unit. Okay, so you can just basically cut it in half because you're assuming this constant rate of depletion for your demand equation, okay? If you're not an econ major, don't stress about the theory of it. Just know you're going to add a half to whatever the cost is. So this is the setup cost for the batch. That's the storage cost for the batch. Add them together and there's your total cost, okay? So total cost, I can write it as C of X. It equals 600X plus 1/2 times 4, that's 2 times 60,000 over X. Before we take a derivative, let's clean this up. So C of X equals 600X plus 120,000 X to the negative first. Now let's take a derivative. So C prime of X equals 600 minus 120,000 X to the negative second. I'm not interested in where C prime doesn't exist because that happens when X is 0 and that's not in the domain, so who cares? So I'm just gonna set C prime equal to 0. So this is a little shortcut. I haven't done this before, but I wanted you guys to see just kind of a quicker way. 120,000 over X squared, right? And then multiply both sides by X squared. Then you have 600 X squared is 120,000. And then divide by 600. That's gone. Bam, bam, 2 zeros are gone. And then you have 1,200 divided by 6. So then we get X squared equals 200. I'm not going to put plus or minus because we're not going to have negative number of batches. So X equals rad 200, which is 10 rad 2 batches. Now we need to verify that this yields indeed the minimum cost. So verify X equals 10 rad 2 yields the min cost. How do we do that, guys? Yes, second derivative test. So let's take one more derivative, right, using that version of C prime. So C double prime. Derivative of 600 is 0. So bring that exponent down in the front. That would be positive 240,000 X to the negative third, which I can rewrite as 240,000 over X cubed, right? And I can tell since I'm plugging in something positive for X, then this is going to be positive, which means my cost function is concave up at that critical value. So indeed, it yields a min. We are good to go. So the number of batches is 10 rad 2. In the beginning of the problem, they said to round to the nearest whole number. Okay, so we can do that. So 10 rad 2 batches is the exact answer, but we're not really going to make 10 rad 2 batches. We need a whole number. Rad 2 is about 1.4. So 1.4 times 10, that's about 14 batches. Okay. There you go. So it looks like more than once a month you're going to be making a batch, right? 14 batches throughout the year. And there you go. So that's how you solve that problem. I think the trickiest thing is coming up with the cost equation. And if you don't, if you haven't taken much econ, the storage cost, the fact that you just slap a 1/2, assuming the cost equation uses average cost. That was a big important factor. Okay, that concludes the video. If you're in my class, I've done all of the optimization problems on your practice exam, so you should be good to go. And give the video a thumbs up, subscribe if you haven't already, and I'll talk to you guys soon. Bye.